This is still a continuation of conjugated substances, and now we'll talk about what is called aromaticity. So aromatic history actually starts with compounds that had fairly strong smell, aroma, hence the name aromatic. But now aromatic has a completely different meaning in organic chemistry than what it normally started with, which is aroma. But anyhow, benzene itself was discovered first by Michael Faraday, 1825, and he found that the CH ratio, the carbon-hydrogen ratio in it was 1:1, which is really very low considering all of the things that we've been talking about, hydrocarbons and alkane, alkene, alkyne. It turns out to be a very low ratio, which means a very high degree of unsaturation. It was later synthesized in 1834, and the molecular formula was confirmed, okay, and it was found to be C6H6. And so anything that had that kind of a low ratio of carbon to hydrogen was classified as aromatic without really understanding what it means and what really the structure was. Eventually in 1866, Kekule is credited for proposing the structure for benzene, and we will talk about in class a little bit more about the history of how it was discovered. But in any case, Kekule is known for proposing this first structure of benzene. Some of the other structures of benzene are quite different, or the proposed structure is quite different than what this is. And he was the first one to propose a cyclic structure in which there was an alternate double bond, single bond in a ring. And so in this case, as we can see that each carbon has only one hydrogen, there is a ring structure, and everything is what we say as perfect. But one thing that he could not explain, okay, is that if you take benzene and you do chlorination on it, and if you have a structure like this, okay, the one that he proposed, then you would end up getting two isomers of the chlorinated benzene. And especially if you get the 1,2-dichlorobenzene. So at one point, the chlorination would be on the single bond, like this. And then in another case, the chlorination would be on the double bond, like this. And so there should be two different compounds. However, when the chemistry was done, it was only found to be one isomer, and he could not explain that. And this came about later then as to what's going on. But what he started with over here with the structure was essentially a very good start. So there are some unusual reactions of benzene which were not expected. So benzene, considering it's such an unsaturated compound, should go on to go the same reactions as alkenes do. However, when benzene was treated with KMnO4, there was no reaction. But alkene with KMnO4 gives us a diol, as we know from our alkene chemistry. But with KMnO4 and benzene, there was no reaction. With bromination also, there was no reaction. So with alkene, it's actually quite a characteristic reaction. You have done this in the lab also, and you know that it's a qualitative test for any kind of an alkene. But with benzene, there was no reaction. However, if there was a catalyst used with bromine and benzene, then the bromination gave a monobrominated product, which really is not an addition reaction, it's actually a substitution reaction. And all the double bonds that benzene initially had, they still remained. So it was not an addition, it was a substitution reaction. So that also got people thinking about, well, benzene is not really behaving the same way as alkene is. So then they thought, okay, then maybe all cyclic compounds which are conjugated will behave like benzene, because benzene is like this, right? And it's conjugated. Conjugated because it is single bond, double bond, alternate double bond, single bond. So that's why it is considered to be conjugated. So I thought, okay, well, then other conjugated substances should behave the same way. But then cyclobutadiene, which looks like this, did not behave the same way as benzene would. And then neither did cyclotetraene, which is 8 carbons with the 4 double bonds. And this was synthesized with great gusto by Willstatter in the early 20th century, and the whole goal here was to study the aromaticity of cyclooctatetraene, but it turned out that it was just like a typical alkene, which itself is a big study. to understand this fact. So once all of this was done, then some other structures were proposed then and said, okay, well, something else is going on. It's not just benzene as in a highly unsaturated compound that it should behave like an alkene. So something else is going on. So then came what we call the modern theory of benzene structure, and in this it was proposed that the benzene structure actually undergoes resonance. Okay, and we know about resonance already, which is the movement of electrons over bonds. And so it was proposed that benzene here will have shifting double bonds. Okay, so here the double bond shifts from here to here, this one shifts to here, and this one shifts to here. So then you have all of these double bonds here. So in which case the structure number 1 and 2 are equivalent. They're not in equilibrium, which means they're not two different structures, but they're actually resonant structures, hence this arrow on the top, not the equilibrium arrow. So it was considered that these two structures then are equally contributing to the resonance structure of benzene. Well then, if that's what it is, then the bond length should prove it, because bond length is the best way to figure out if you have resonance going on or not. And it turned out that that is true, that there is resonance going on, because if you had a double bond and a single bond, you would see two bond lengths, one for a double bond and one for a single bond, all right, which would be 1.47 for a single bond and 1.33 for the double bond. The double bonds are shorter, but that didn't turn out to be the case. It was neither of these, and it turned out it was a whole new bond length, which is in between the two. So if it is in between the two, it means that these electrons are highly delocalized, which means that the resonant theory is correct. Okay, so if there is a lot of delocalization going on, then it means electrons are everywhere. It means that the bond length is going to change. So then we can start representing benzene as not in a double bond, single bond manner, but we can also write it like this, because this shows that the electrons are highly delocalized all over the 6 carbons. So then there is the MO theory. How can we forget the MO theory? All right, in the molecular orbital theory, there is of course the orbitals of p that are overlapping. Now remember, with the carbon, each of the carbon in benzene, which is double bond, single bond, double bond, single bond, is all sp2 hybridized, because it has one double bond and two single bonds. So it's sp2 hybridized, which means it has one p orbital. So there are pi bonds in there. So there are 3 pi bonds in there, which means that each of the carbons that you have in there, each of these carbons is sp2 hybridized. So each of these carbons has a p orbital. So if it has a p orbital, let's go back to our MO theory that we talked about in conjugation. And we said those orbitals will overlap as in the positive regions and negative regions. And so this is how the overlap will actually occur, where if all the positive region pi orbitals were on one side, then this is what you would see, and the negative would be at the bottom. And you can think of it as a donut if you want to, where the benzene ring is a planar ring, it's flat, and then you have electrons on the top and then orbitals at the bottom, where you have electrons on both sides. So that's what it looks like. And of course, here is the ring, the delocalized ring. So this is one of the combinations possible. And then the other possibility would be when you have the 3 of these orbitals overlapping and the other 3 are not, in which you case, or they are, but it's the opposite charge. And so you have one node, okay, in this case. So that is a little bit more unstable than when everything is bonding, because remember, we have no nodes, that's the most stable structure. So then in this case, this is a little bit of a higher energy structure, and then we can differentiate it even more when you have even more nodes forming, which means that there is more opposite regions that are not able to overlap. So you end up getting something even with more nodes like this, okay, and this. And then there is one on the top which is then completely anti-bonding, okay, where each of the lobes is completely on the opposite sides. So these are the 6 possibilities, okay, of finding electrons. Where would you find the electrons? You would find the electrons in the most stable region, which is actually the bottom one. And remember, there are 6 electrons because there are 6 p orbitals. So if there are 6p orbitals, you would have 6 electrons. So the 6 electrons are not found in these 3 over here because these are all anti-bonding because of the node. You find them at the bottom 3 because that's where you find more stability. So this is how the structure looks like for benzene then. And it's not that there are no electrons on the top part of benzene. This is just the molecular orbital theory. And the nice thing that we've done with this kind of a circle or a benzene circle, these are called Frost diagrams. And the nice thing is that you can actually place these orbitals, anti-orbitals, and bonding MOs right on where the carbon should be or where the p orbitals are, and then designate where the electrons will be found. And this is where they're found. And all the bonding, remember there are 6 electrons, and you will find them right over here. So which means that the non-bonding line is very, very nice and clearly drawn in the sense that you have perfect symmetry going on where you have 3 orbitals that are completely vacant and 3 that are completely occupied. This is known as a Frost circle, and it's really very helpful in determining what or how these molecular orbitals are occupied in cyclic conjugated substances. Okay, so we'll see another one. So here's the one for cyclobutadiene. Okay, and remember we said the cyclobutadiene does not behave like benzene. It's a little bit different. Okay, it's very reactive, and that also is of course because of its highly strained ring. But even otherwise, it doesn't quite behave like benzene, which means that it does not add on bromine or KMNO4 and all that. So in this case, here is the Frost circle. Okay, this is what it would look like. Now you have 4 carbons in there, 4 carbons, and you have 2 pi bonds, which means you have 4 p orbitals. If you have 4 p orbitals, these are the different possibilities of those 4 p orbitals. One in which all the positives are on one side. That's the total bonding orbitals. And then here you have the other possibilities of the bonding and the non-bonding. So for example, right here, it's the bonding, and then here it is the anti-bonding. So you have one node over here. So with these positives, and then there are the negative regions on the other side. So not being able to overlap. And here's the other possibility. Now these two are going to be almost equal in energy because it's just a matter of which carbons you're talking about, all right? And then of course the last one where everything is up and down, up and down, up and down, so nothing is overlapping and everything is anti-bonding, and you have more nodes than any of the ones before. So if you turn the structure around, instead of a square, you look at it as a diamond. And then try and fill in electrons, which remember in this case there are 4 p electrons in there. So the 2 will go right here at the bottom because this is the more stable structure. This is the MO, complete MO, okay, completely bonded molecular orbitals. And then you'll find 2 electrons right here, okay, in the middle. And again, we follow Hund's rule and all that, where you have to put in 1 electron each before you start pairing them up. So in each of these anti-bonding orbitals, you will place 1 electron. And the top one is empty because there are no more electrons left anyway. There are only 4 electrons to put in the p bonds or in the pi bonds. And in this case, when you have a perfect symmetry going on, in that perfect symmetrical line in the middle, you actually have electrons. Okay, in the benzene structure, there were no electrons. There were 3 on the top, 3 at the bottom. But here, you actually have electrons in the non-bonding line. And that is what leads to the little instability that cyclobutadiene has. Okay, and so this is the Frost circle for cyclobutadiene. And here is the Frost circle for cyclooctatetraene. Now remember I just said a few minutes ago that cyclooctatetraene also did not behave like benzene, even though it has 4 double bonds and it is highly conjugated system, but it does not behave like benzene. And now you can look at it and see, okay, why it does not behave like benzene. When you draw the Frost circle for cyclooctatetraene, it is very similar to cyclobutadiene in the sense that you have the complete molecular orbitals over here which are completely filled in, but then on the anti-bonding line you have 1 electron each, whereas in benzene you don't have that. Okay, so you can pretty much draw out this kind of a frost circle for any cyclic compound and then figure out if it is going to be aromatic or not. It turns out benzene is aromatic, whereas cyclobutadiene and cyclooctatetraene are considered to be, well, not like benzene, so not aromatic. So then the question still is, why is this so? Okay, why is it that benzene is still behaving differently? Okay, we know the MO theory, we know all of this now. We also know there is conjugation going on, but there is conjugation going on here also. So what is it that makes it different? So then come some rules, okay? And these rules then really help us determine what is going to be aromatic and what is not, okay? And so there are three things that we talk about usually in aromaticity. One, of course, is aromaticity. The other thing is anti-aromatic, and the third one is non-aromatic. So we can classify any compound in any of these three categories, okay? And so for aromaticity, for any structure to be aromatic, it must be cyclic and it must have conjugated pi bonds. And benzene falls into that range, but also does cyclooctatetraene and cyclobutadiene. Okay, so obviously they fulfill this category. Then each atom must have an unhybridized p orbital. Well, benzene has that, and so does cyclooctatetraene. Okay, then the third criteria is that the p orbital must overlap continuously. Okay, and continuously meaning that the structure should be planar. That is the key thing over here. And cyclobutadiene actually is a planar structure. Cyclooctatetraene should be also planar because of the angle strains and all that. So all of these three things, okay, which are very common, very obvious, that you can see that the structure is conjugated, it has unhybridized p orbitals, and it is a planar ring. All of this is being followed so far. The last thing which really makes the big difference is the Hückel's number. Okay, and we'll talk about Hückel's number in a minute, but if the cyclic structure does not have the Hückel's number, then it is not going to be aromatic. Okay, so then let's talk about anti-aromatic and non-aromatic and get it over with. Okay, so what the heck does it mean for something to be anti-aromatic? Anti-aromatic is anything that is cyclic conjugated with p bonds, but it doesn't have the Hückel's number. So it doesn't have the last criteria. That is how you would say something is anti-aromatic. So for example, benzene is aromatic, but cyclooctatetraene and cyclobutadiene, those are anti-aromatic because they follow all the rules except for Hückel's number, which we'll deal with in the next slide. Non-aromatic compounds are not going to have any of these, more than one of these or two of these things, which means they may be not cyclic, first of all. So any kind of an alkene, which is a straight chain, is definitely not going to be aromatic. Anything that does not have unhybridized p orbitals will not be aromatic. Anything which is, not planar is not going to be aromatic. So those are going to be non-aromatic. And then we'll do some practice also to see how to classify these compounds. Okay, but these are the criteria that you have to keep in mind as to how to classify compounds. So then let's talk a little bit about the Hückel's rule, okay, or Hückel's number. And the Hückel's number has to do with the 4n+2, as you saw in the previous slide also. And the 4n+2 has to do with the number of pi electrons that are present. Not pi bonds, pi electrons, okay, which means the p orbitals that we're talking about. Even in the previous slide we talked about that each carbon should have a p orbital which can then overlap. All right, so there should be a continuous ring, okay, of overlapping p orbitals. So each carbon needs to have a p orbital, whether it is hybridized or unhybridized, doesn't really matter. Okay, so n here, 4n+2, n here is 0 or 1, 2, 3, 4, 5, 6. It can be any number then after that. Okay, but n can also be 0. So let's see what numbers we come up with. Okay, so if n is equal to 0, then 4 times 0 plus 2 is then 2. Okay, which means that any compound which has 2 p orbitals will be aromatic. Okay, well, there is no compound like that, okay, because you need to have 2 electrons or 2 p electrons, which means you need 1 double bond. If you need 1 double bond, then the smallest structure possible for that would be a 3 carbon structure. But then even if you have the 3 carbon structure, you still don't have conjugation, because that is another requirement of aromaticity. So this does not really exist. All right, so which means this number is mute. When n is equal to 1, then the number of pi electrons that are required would be 6. Okay, so if any compound that has 6 pi electrons in it, it will be aromatic, which is benzene. Okay, benzene has 6 p electrons, or the pi electrons. 3 pi bonds, 3 times 2, 6. Okay. When n is equal to 2, that means you will have 10 electrons in it. And with the 10 electrons, it can be aromatic. However, this is one of those exceptions, not exception, but it kind of does not follow into the aromatic category because it's not a planar ring. How would you know it is not a planar ring? Well, sometimes you just have to make a model, okay, and then see how it falls. All right, so in this case, it's not going to be aromatic because it's not a planar ring. However, the number 10 is aromatic. So any ring that is planar and has 10 pi electrons will be aromatic then. Okay, so you can't rule the number out. It is just that a hydrocarbon with 10 carbons is not going to be aromatic. When n is equal to 3, then after doing the calculation, it turns out you should have a total of 14 pi electrons, and that compound is aromatic. So we are following some trends over here. Okay, for 2 it does not exist because you don't have conjugation also, and it's very hard to make that compound. 10 is not aromatic, and this is for a hydrocarbon because it is not planar. Okay, and so if it is not planar, it means that you have no overlap going on. So that doesn't really help with the aromaticity. Okay, and so then here are some of the other aromatic compounds which will follow the Hückel's number. All right, so 6, of course, I have not drawn here because you already know the structure of benzene. And then here is 14, 16, and 18. All right, 16 is not a Hückel's number. All right, if you see that all these numbers are separated by 4, obviously because you are multiplying by 4. Okay, over here each integer. So you add 4 electrons to each, and that's how it becomes aromatic, which means that 4 here is not going to be aromatic, 8 is not going to be aromatic. 4 was the cyclobutadiene and 8 was the cyclotetraene, and that was not aromatic. So 12 is not going to be aromatic, and then 16 is not going to be aromatic. However, 18 will be aromatic. Okay, and so this is how you will kind of decide whether something is going to be aromatic or not. Okay, Hückel's rule is the first one that you generally end up following and seeing if it has any of these number of electrons in it. Then you say, okay, now I can look for the other things like, is it conjugated or is it, planar, those kind of things. All right, so that is the advantage of Hückel's rule. Okay, and Hückel's rule was established only in the 20th century, and that's when the whole concept of aromaticity changed. Now, aromaticity has nothing to do with the smell. Aromaticity is now to do with Hückel's rule and the fact that you have all of these rules that are being followed so that a class of compounds behaves like benzene does. That is what aromaticity means now. So anti-aromatic compounds, well, we talked about it already, so let's just review this really, really quick. There are planar cyclic molecules, and they will have 4n electrons, not the 4n plus 2. Okay, so which means they're not Hückel's number. That is the key thing over here, all right? And so the two examples we talked about was a cyclobutadiene and cyclotetraene, all right? And so they don't really behave like aromatic compounds. They don't follow Hückel's rule. They would be called anti-aromatic. Now there are some ions also which can be converted or which can be formed, which will behave like aromatic compounds. The criteria for aromaticity, remember, is planarity, conjugation, Hückel's number. Those are the rules. The rule is not whether you have an anion or a cation. That is not the rule. The rule is for electrons. How you get those electrons is a whole different thing. So if you have a cation, you can still have aromaticity, or an anion, you can have aromaticity. So let's look at this one. A cation with an empty p orbital in this case, okay, where you have a 5-membered ring. Okay, so if you look at something like this, all right, so if you have a 5-membered ring like this, cyclopentadiene, all right, and then you remove 1 hydrogen, okay, from it. If you remove 1 hydrogen using a base, okay, which means that it is being picked up as a proton, which means if it's being picked up as a proton, it is leaving its electrons behind, And so here are the electrons. Okay, so now what does it mean for the system? Okay, this one was not aromatic. Okay, it's not even anti-aromatic, it is non-aromatic, because you have the double bond here, you have the double bond here, but there is no place for conjugation right here. Okay, because this is a single bond and a single bond. So this is not a conjugated system, so it's not an aromatic system. However, now that you've created this extra electrons, now these are in an orbital, okay, which would be the p orbital, because that's where carbon is found, in the p block. So now you have these electrons in the p orbital. So now these electrons can delocalize over the whole ring, and if they can delocalize, then you can count the number of electrons and see if they are Hückel's number, and they happen to be Hückel's number, which is 6 pi electrons. Just because you form an anion does not mean it's going to be aromatic, okay, or an anion or a cation for that reason. Just because you form that doesn't mean it's going to be aromatic, okay. It has to follow the Hückel's number also. All right, so this one turns out to be, if you push in 2 electrons in it, then it does have the 6 electrons, and now these are conjugated, and so then the cyclopentadienyl ion, this becomes aromatic, which means it's going to behave like an aromatic system, which means it will not undergo addition reactions, it will undergo substitution reactions and all of that good stuff. Okay, so that is one example. Here is another example. This is tropylium ion. Okay, so here again we have a very, it's a non-aromatic system. Again, you have conjugation here, here, and here. So this is a conjugated system here, but not conjugated here. So as a cyclic compound, as an aromatic structure, it is not aromatic. It is conjugated, but not aromatic system. Okay, however, if you remove this OH from here, okay, and it goes away with the electrons, then you're left with a cation. And a cation means that now you have an empty orbital. An empty orbital then leads to delocalization of electrons over here and then from here. So which means that now these 6 electrons can delocalize all over. So now this becomes a 6p electron system. Okay, 6 pi electron system. And so now this is going to be aromatic, whereas this one was not aromatic, right? But now this one is going to be aromatic because of this cation over here. All right, so then let's look at cyclooctatetraene again. So if you form an anion, for this one a dianion, okay, for this one it will become aromatic because now it has 10 electrons. All right, with the 8 electrons it was not. Okay, remember the numbers are 2, 6, 10. Okay, so 8 was not, but now that it has 2 extra electrons in there, now it is a 10 pi system. So now this will be an aromatic system. It will undergo substitution reactions, not addition reactions. Okay, so you can change the properties of a compound to make it aromatic or anti-aromatic or non-aromatic, okay, just by converting it into ions. So then there are some other compounds also which are aromatic, and they're not hydrocarbons. They're not pure hydrocarbons. These are called heterocyclic aromatic compounds, and heterocyclic means they're cyclic compounds with the heteroatom. Heteroatom is anything other than carbon and hydrogen, okay? Because for us, organic chemistry, everything is carbons and hydrogen. So anything that is not carbon or hydrogen is a heteroatom. Chlorine, sulfur, oxygen, all of these are heteroatoms. So in this case, we're looking at nitrogen containing compounds, all right? And so you can have nitrogen in a compound also and have aromaticity, okay? So for example, in this compound, this is called pyridine, and pyridine is an aromatic system, okay? So what happens in this case is if you don't look at the nitrogen over here for a second, then it looks like benzene, right? So which means it has the 6 pi electrons, and you have conjugation going on, planar ring and whatnot. Then when you put in the nitrogen in there, now you actually have extra electrons. However, these electrons will not participate in the resonance, okay, which means in the conjugation. So if they're not participating in the conjugation, then this will still be an aromatic system. This will not be an 8 electron system. This will still be a 6 electron system. And so then you're wondering, well, how does it know when to participate, when to not? Well, the deal is that aromaticity leads to a lot of stability, okay? Conjugation, delocalization, All of this leads to a lot of stability. So whenever conjugation is possible, it will happen. Whenever it leads to aromaticity, it's going to happen. So if in this case, the delocalization of these electrons was not required for stability, well, they do not need to delocalize then, okay? And so this will remain as an aromatic system without the help of these electrons. However, in case of Pyrrole, which is a 5-membered ring with the nitrogen here, now in this case, there are only 2 double bonds here. So if there are 4 electrons here, now the 2 electrons can be pulled in from the nitrogen here. So these electrons will start participating in the conjugation, and once they start participating in conjugation, now you have the 6-electron system. And if you have a 6-electron system, boom, here we go. We are aromatic. However, if you remove those 2 electrons from there, make it a cation here, make it a salt, no more electrons, no more conjugation, okay, which means that now this is an anti-aromatic system, all right? So this is aromatic by the way of lone pair of electrons, and this one is anti-aromatic. Remember, this is cyclic, it just doesn't follow Hückel's number. So here are some other compounds, okay, which are also aromatic, and they also have nitrogen in them, okay? And so these electrons here, the lone pair of electrons here, they can choose to be participating in the ring or not participating in the ring. One other thing that is key about nitrogen compounds is that nitrogen containing compounds are usually bases like ammonia, okay? We know that anything like ammonia with ammonium hydroxide, those are all bases. Amines are organic bases. And so one of the things that makes bases bases is the donation of an electron pair, which is a Lewis base. So here we have a nitrogen that can actually donate the electrons and be a base. Okay, so by the way of donating its lone pair of electrons. So here in case of pyridine, for example, these electrons are not participating in conjugation, in resonance, in aromaticity, which means if they're not participating in all of that, this nitrogen is a little bit basic. So pyridine is actually a little bit of a basic solvent, all right? However, in this case where you have pyrrole, where these electrons are participating in the conjugation, now they're occupied. And if they are busy over here, they cannot be donated as a base, which means that pyrrole is not basic, okay, in properties. So pyridine has slightly basic properties, whereas pyrrole does not, okay? So which means that just by the way of aromaticity, now you have also changed the acidity and basic properties of any compound. So here also, these are examples of where electrons can participate or not participate in aromaticity. So here the electrons don't need to participate because you already have the 6-electron system going on, which means that pyrimidine has 2 lone pair of electrons. Okay, imidazole, which also has 2 nitrogens in it. Now one of the pairs can be participating, the other one does not. Okay, and so which one is participating in the resonance? This one is, okay, or this one. It's this one. Yes. So if it's this one, then these nitrogen electrons are going to be then the basic ones. This one is not the basic nitrogen. This is where the reaction of acid base is going to take place, not here. Similarly, you can look at purine also and then decide which nitrogen is going to be basic and which one is not, which is involved in aromaticity, which one is not. Of course, generally you can see the one with the hydrogen it has the one that has electrons that are participating in aromaticity. These molecules are also here for another reason. You will find heterocyclic compounds in biochemistry also. Okay, so you might as well become familiar with this. So for all of you who are going to go on to biochemistry, you will see these molecules again, okay? And so you will have to make this determination as to which nitrogen is basic and which one is not as you go on. There are some other heterocyclics also and some different kinds of aromatic compounds. So pyrrole we already talked about. So in case of pyrrole, these nitrogen electrons are participating in the aromaticity, making pyrrole an aromatic compound. Here is furan, and remember we've talked about tetrahydrofuran, and this is where it actually comes from. So in this case, in the furan ring, you actually have oxygen, and oxygen has 2 lone pair of electrons. And so in this case, oxygen gives only 1 lone pair of electrons for participation for aromaticity. The other lone pair is not involved. in aromaticity. Same thing with sulfur. In this case, which is thiophene, one electron pair is involved in aromaticity. So all of these compounds are actually aromatic in nature. Okay. Some of the other aromatic compounds are like the typical and true hydrocarbons. Anything that has benzene and anything which has fused benzene rings, they will automatically be aromatic. Okay, so whatever looks like benzene, even though sometimes you can see and you are trying to figure out how do I draw the double bonds, am I able to get the alternate double bonds or not? But no, if you have fused benzene rings, they're all going to be aromatic. So naphthalene, anthracene, pyrene, benzpyrenes, phenanthrene. These are all fused benzene rings, and these are all going to be aromatic. Naphthalene is only one kind because you only have two benzene rings, but when you have three benzene rings, anthracene and phenanthracene, these are phenanthrene. These are both constitutional isomers. Okay, with the benzpyrenes, there are many possibilities because now you have five rings, and so this becomes very, very common. Or excuse me, it'll give you many constitutional isomers. So these are some other compounds which are automatically aromatic. Now we'll talk a little bit about the applications of aromatic compounds in class also, but just to give you a general idea, you find these compounds all the time, okay, everywhere. There, pyrrole, for example, is very commonly found in porphyrin, which is the starting material for chlorophyll and for hemoglobin, and so you will find the pyrrole there. Naphthalene and all of these are found in petroleum products a lot. Benzpyrene is very notorious and it is found in cigarette smoke. This is considered to be one of the most potent carcinogens out there. We'll talk some more about aromatic compounds in class also, okay? But they're very, very bad compounds, very toxic. So the key things that you need to know regarding this little portion here is why benzene is aromatic. You should be able to prove to me, right? Give me all the reasons for it. You should know the MO theory, which means that you should be able to look at a structure, a cyclic structure, and draw a frost structure from it, and then see if it is going to be aromatic or not. Decide whether a compound is anti-aromatic, non, etc., etc., and you should be able to figure out from ions and then of course the other compounds, okay, and see if it's going to be aromatic or not. That is aromaticity.